Okay, welcome into our lesson on slope fields. We've got a little coordinate axis on the right that we're going to use in a few minutes. And then I've just got the title on here of slope fields. We're just going to work through one problem in this particular video. And that problem that we're going to look through is a differential equation. And we're going to keep it pretty simple in terms of what our differential equation is. We're going to say y prime equals 2x. So y prime equals 2x. Another way we can write that is dy over dx equals 2x. So one of two different ways that you'll see slope equations or slope fields presented. And again, the idea here is we have an equation that defines what slope is at any xy coordinate. So what we're going to be looking to do is construct this thing called a slope field. And to do that, what I'd like you to do is go and you can just freehand a graph. It doesn't have to be super fancy. And we'll just tick off 3 in each direction, try to keep them somewhat even, 3 in each direction. And what's going to happen then is we could trace in little sample slopes at any of these spots based on the equation. As if, for instance, if I were to go to the point 1, 1. So that's right there, 1, 1. And I said at that specific value, or that specific spot on our coordinate axis, what's the slope of this function? And we don't know what the function is. So y equals question mark. We don't know what the function is, but we do know what its slope is doing. So that's what a differential equation or a slope field equation does, is it tells us what's happening with the slope. So this is saying take whatever the x value is at your coordinate and multiply it by 2. So at 1, 1, the x value is 1. So we'd multiply it by 2, and that would give us a little slope snippet of 2. And so I'm going to draw that in there with a red pen. And again, we talked about this in the last time we were in class together. Drawing a slope line of 2, that's actually pretty good too, I think, is challenging to do. We're just drawing a little tiny snippet of it. And what the AP is going to ask, if they do ask you to do something along these lines, is they're going to give you the integer coordinates with little dots at them. So let's go and do that with our graph. So at each integer coordinate for the xy values, they're going to put a little dot. And then they're going to ask at each one of those dots, draw a little slope slash in. And I picked this 2x because it's a bit easier to get our heads around than when there's both an x and a y, which is what we did in class on Monday. So I'm just going back over this idea with something that's maybe a little more bite-sized. And what's happening then is everywhere where x is 1, you're getting a slope of 2, no matter what the y value is. The thought process there being the derivative equation is just 2 times x, so it doesn't have a y in it. Because of that, what we can do is say, okay, anywhere where x is 1, we've got a slope of 2. So I'm going to attempt to draw that same amount of slope as best I can at all the places where my x value is 1. So it's a whole bunch of stripes that look like that. And then you can probably think about, hey, what's going to happen here as we move to the right? So we're going to say, okay, let's go over to 2. If we went over to any point that has an x value of 2, any point that has an x value of 2, we're going to get slopes of 4. So instead of getting a slope of 2, which is what this entire set of, oh my goodness, that jumped around on us, what this entire set of slopes is, we're going to get slopes of 2, or of 4 rather. So here's our set of slopes of 2. This set is going to give us a set of slopes of 4. So steeper, right? Tough to draw the 2 versus 4 distinction. I'll do it as best I can. Certainly steeper. If we go to 3, it gets even steeper yet. It's 6. And at some point, it just gets really challenging to differentiate. And you can see my 6s don't look much different than my 4s. The AP, the way they grade it, if they were to choose to grade this, is they just say you've drawn in the correct positive slopes. And the reason they say positive is in this case, if we were to go over to negative x values, so any negative x value, like negative 1, we're going to get a set of negative slopes. And they'll just be the mirror image of the slopes on the right, but they'll be all negative. So again, I'm just doing the vertical stripes of slopes because that's where all the slopes are going to be the same. No matter what the x or y value is, you got the same x value. And so now I'll go to my negative 2, and that's going to give me a set of slopes of negative 4. And I'll go to my negative, what would that be, negative 3. I'll get slopes of negative 6. And that really is it. In this case, we can do 0 too, where x is 0 up and down the y-axis. We get slopes of 0, so we get little horizontal lines. like that. And you could fill in the spaces in between. You could say, okay, what's this thing doing at 1/2? Well, at 1/2, so the spot between 0 and 1, that vertical stripe set would be a slope of 1. So I've not got it dotted in here, but there's no reason we can't do it. You get this set of slopes, and then you'd have a mirror image of a negative set. And again, the AP traditionally has stuck simply to integer values, but you could populate this thing literally at as many values as you wanted to, coming up with a slope field. But by hand, if you're asked to do it, you're going to have these slopes only at the integer coordinates, and that's it. And that is a slope field. So what this thing is doing is it's giving you a sense of what the function would look like if you knew a value on it. So without knowing a value on it, this is just a vague set of slopes that just define a path for the function. But in reality, if we're looking for a specific value, we have to be given an initial condition. So an initial condition is simply saying, okay, let's pin down where this thing starts, and it can be anywhere. They can give you any initial condition. So say we went y of what we could say y of 2 equals -1. So that means our y, or another way to write that would be f of 2 equals -1. A lot of times they'll use y of 2 equals -1, but it means the same thing. Then what you're saying is, okay, start your graph at the point 2, -1. That is an actual point on the function. So you're saying, I've got this theoretical set or hypothetical set of slope fields that I can trace, but in reality, only one of them is going to provide the path based on the initial condition. So there's the dot. It falls right there. If I move from that dot to the right, it's going to be moving up at ever steeper slopes. If I trace it the other direction, I've got to follow the slope field. It's going to go down, 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 eventually going to bottom out, and then it's going to pop back up. And that shape should look really, 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 really familiar. That thing looks an awful lot like a parabola. And in fact, if you think about or go back to this initial expression, it probably isn't that hard to see why a parabola works, and not just any parabola, a very specific parabola. So in the first section in this chapter, we talked about, hey, here's what a differential equation is. It's just an equation for a derivative, and it has these things called solutions. So this one, 2x, has solutions to it. What a solution is some y equals equation. So y equals something is our solution. And in this case, if it shouldn't be too big of a leap to say, well, y equals x squared would be the solution here, because if you were to take a derivative of this, y prime is 2x. That's what the differential equation is saying. So y equals x squared would be a function solution to this curve, or to this slope field, but the slope field itself is just a set of little slope snippets that you can follow based on whatever initial condition you're given. And in this case, I just arbitrarily chose 2, -1. You could choose any dot you wanted, and we can put one more on there. So why not? I've got all these colors. Let's put another one on there. Let's say we said, you know what? Let's do f of -1 equals 1. So that means -1, 1 is on our graph. Well, -1, 1's right here. And if we trace from there to the left, you can see our slopes are going to get steeper. We trace from here to the right, our slopes are going to get less steep, and we're going to look something like that. Again, this is just one way in which we can use a differential equation. It's a very rudimentary thing to draw a slope field. And then you'll be given something called an initial condition that allows you to sketch in what a functional answer would look like. And ultimately, we can say in this specific one, because it is such a simplistic one, just kind of eyeballing and guessing, hey, here's what the equation is for this particular parabola. And really, actually, if we're thinking about it, it could be any y equals x squared plus c. So anything moved up and down, because when you take the derivative of that, you get 2x and the c goes away. So I could have been a little more clear. So there's actually an infinite set of potential equations that work for this, which is why we get all these different parabolas, why I get a blue one that's shifted down, a green one that's kind of up normal where we're used to seeing it. But any y equals equation, y equals x squared plus 3, y equals x squared minus 7. These would all be potential answers because they would all work or fit for the differential equation. So that is the idea of these slope fields, is that you create a set of slopes that would work, you pin down an initial condition, and that then defines what your plus C is. Right now, that's all you need to know how to do with them. Draw the red slope field, trace in an initial condition. We'll eventually get to the point where we're solving for specific equations that fit with the slope field. So that's it. That's slope fields. Hopefully it helps understand the concept, and we'll follow up with some practice problems.